refers to offshore, the one that's in the ocean or in the sea. So we see that every year it was almost the same until a little increase in 2019, and the new installation in 2020, it was almost doubled. So it was a real increase pushed mainly by China and the US during this year. I put all the references here, and I will share a PDF of the presentation after the meeting. You can click the link and see the reference anytime you want. If we look at these new installations in 2020 by region, we can find that for Asia and the Pacific, it's almost more than half, it's 60%. The one afterwards is Europe, and then we have North America and Latin America and the Caribbean, and then just 1% for whole Africa and the Middle East. And if we look by the top 5 markets, the green one here is the US after China, and then the rest of the world. So we can see where the technology is going and how it's developing. And historic development during from 2001 until 2020 for the new installations, we can see that every year it's going more and more installations. So you can imagine how the accumulative one is going to be. And for 2020, you see very large amount of wind power was installed. So what about Egypt? So we can see that the European Bank for Reconstruction and Development is supporting Egypt in this field, and there is a big fund for that, and there was a visit from the president of this European Bank to study different opportunities in Egypt and to help Egypt with that. And we can see that a big player in Egypt in this field is the British University in Egypt, from which we have our guest, and they were signing a protocol for renewable energy field in Egypt. Also here, the British University is building turbines for the countryside, trying to make some projects in the countryside, especially in places that are so far away from energy generators, so they can get the energy from the wind. And until now, Egypt has moved from the 145th place to the 77th place between countries that are producing electricity in this rank. So there is a difference that's happening. If we look at the map, here's Egypt is producing at the moment about 1,465 megawatts. And even KU Leuven in Belgium, they are expecting that if Egypt and whole area of northeast of Africa is going to use solar and wind energy power, there will be no fight about the dam in Ethiopia, for example. There will be no conflict. So it could elevate. This conflict could be elevated by massively expanding solar and wind power in this area. And the previous report that I showed you parts from, they were expecting Ethiopia to be one of the biggest potential countries for increasing wind power in this area. So now I would like to introduce for you Professor Mustafa Chazli. He's the director of Center of Advanced Materials at the British University in Egypt. If you click, after I send you this version, if you click on this Google Scholar, you will go to his publications in this field. He got his bachelor and master degree from Cairo University in mechanical design and production engineering. And he also got his PhD from the US, from Case School of Engineering and Case Western Reserve University in Ohio. And during his stay in the US, he was so active, he got a fellowship from Case Prime. He was working as a research associate, and also he worked afterwards as senior research engineer at Goodyear Tire and Rubber. Afterwards, he returned to Egypt, but before that, he was also a member of the American Society for Mechanical Engineers. He worked in Egypt as assistant professor at Cairo University, and then worked as professor of at the Mechanical Engineering Department and director of the Center of Advanced Materials at the British University in Egypt. Such a wow career. All my respect to that. And he also gives industrial consultations and training through both the British University and Cairo University. So now I will let the speaker to Professor Mustafa. I will stop my sharing, and you can share now your screen, and we can start with your presentation.
Okay, thanks, Dr. Mahmoud, for your kind presentation and nice words. Hello, everyone. I hope you are doing fine in these hard times, and I hope you will enjoy my presentation. As you will see, I have like around 70 slides, which is a quite large number for this short period. But as you will see, the presentation is more of a storytelling presentation. It's oriented for general audience. There is no in-depth scientific content, just touching on FUI only. Just I would like you to enjoy it. And then at the end, if you have any question, I'll be glad to answer your questions.
Did you start the sharing?
No, not yet. Not yet. Okay, can you see my presentation now, Dr. Mahmoud?
It's coming. Yes, yeah, I can see it.
So today I'm going to tell you our story at the British University in Egypt. We started working in wind energy sector around 2008, 2009, and I was glad at this time to join the university as an assistant professor or lecturer, and at the same time I was actually, it was my pleasure to work with Professor Yahya Bahid-Din, which he is a well-known scholar in the area of composite material and large-scale modeling. So basically, before that, I didn't know anything about composite material. I used to work on dynamic behavior of material, simulating events like blast loading, high strain rate deformation. We worked I have some work on behavior of ice at high strain rate, just to simulate, the cases similar to Shuttle Columbia experience during the takeoff. It was one of the failure cases we investigated. So basically, I did not touch composite material before that, but when I joined, actually, it was my good time actually to work with him. So I have to give him credit, to what we are doing right now at the British University in Egypt. Today I'm going to first give a brief introduction to wind turbine blades, basically going through some of the requirements, the anatomy of the wind turbine blade, and then we'll discuss go through the development phases at BUE. So actually we experienced 3 phases of development at BUE. First, and when we started around 2008, 2009, we worked on reverse engineering of existing blades, and I'm going to explain that and why did we work on reverse engineering of existing blades. And then the second phase, we actually started the design and fabrication from scratch for some wind turbine blades to fit for specific applications. And then finally, we actually worked on the whole turbine. So basically, we designed and produce prototype for small-scale wind turbines. And I'm going to mention why did we focus on small-scale wind turbines. And then we'll see that as you will see, most of the work we did in this area, it was more of a technology development. I mean, the technology is there, but you cannot get this technology easily because it's a know-how, and it's every company has its own know-how, has its own trade secret. So basically, they will not share with you their trade secret. So you have to develop this technology by yourself. However, as we work in this technology, we find some research areas that needed development, and we're going to mention two of these areas, which are the analysis of bolt connection loaded intention, and we will see that there are we have a motivation actually in the design that forces us to work on this topic. And the second is the repair of incomplete infusions and dry spots, and also we'll mention why we worked in this particular areas. But before we start, first we have to acknowledge the contribution from different funding agencies in Egypt. First was the European Commissioning through the Research, Development and Innovation Program, both cycles, Cycle 1 and Cycle 2, for their generous contribution. Also the Science and Technology Development Fund of Egypt and the Academy for Scientific Research. Basically, so most, all the work actually that you will see were sponsored by one of these funding agencies. Also, we have to acknowledge our industrial partner, because without them, some of the technology we were not able to achieve. So basically, our first industrial partner was Bakir Plastic. Bakir Plastics was the first company to work in composite materials in Egypt, like starting in the 1960s. But unfortunately now they went out of business. I mean, for other reasons, not. It's a family business, so basically they split the business. Also, Arab British Dynamics, which is a subsidiary of Arab Organization for Industrialization, and Mesr for Environmental Technology, which is a subsidiary of Mesr for Commercial Vehicles, or MCV, which is now known as MCV Energy. Also, I have to acknowledge, what I'm going to present is not my own work. It's a contribution from different people working at the British, working or still working or worked at the British University in Egypt, and in particular at the Center for Advanced Material. So we have a huge list of PhD holders, professors, and also a large number of engineers and technicians. Okay, so now, what are the challenges of wind turbine blades in particular? First, stringent design and assessment requirements. Now, if you'd like to design a wind turbine blades, then you have to follow the design procedure by IEC, which is the International Electrotechnical Commission. So when you look into the design practice or design code by the IEC, you will find you have so many design load cases that you have to test your design against. And then after you are done, then you have to go through certification and testing. So basically, it's not an easy design and implementation process. And at the end, actually, I'm going to mention this is one of the challenges that we still have in Egypt. Design is fine, you can do, fabrication is fine, but certification and testing, it's actually a roadblock for us. Know-how, again, the know-how is not available in literature, so you cannot go into a textbook or a published article to get the know-how for the fabrication. Design, you can do it, through the IEC. There are open source software. You can find it at the Renewable Energy Center in the United States. So they have TurboSim and other softwares that are used in the design of the wind turbine blades. So basically, every company has its own trade secret, so they will not share this with you. Even if you talk with people that used to go visits for like training in other countries in renewable energy, when they get into the fabrication facilities, like a dead zone, so you don't know what they are doing exactly. Innovation and certification and competitive price are a must. So basically, you cannot produce a blade that's very expensive, no one would buy it. And to be able to sell it, you have to go through a certification. So no one will buy your blade without a certification from a third party, like for example, TUV or GL. So you have to get their certificate to be able to sell your blade. Now, again, one of the challenges also is that as we increase the size of the blade, the weight increases significantly. So I give you an example that we worked with. When we did a design for a 10-meter long blade, the weight was 220 kilogram. Now, when we did a design for a 25-meter long blade, which almost 2.5 of the older one, the weight was 2.5 tons. So basically, the weight increased almost 10 times. Okay, so as you increase the size of the blade, the weight increases. And as you can see now, the smallest, actually, when they started in 85, the rotor size was 15 meters. So basically, we are talking about a blade with a size of 7 meter approximately. And it used to generate like around 500 or 50 kilowatt. And as you can see, as the time passes, now the size increases. And when you compare that to the A30 Airbus with a wingspan of 80 meter, okay, we have blades that's larger than this size. Okay. Also, the relationship between the blade length and the weight, as you can see, as we increase, the weight increases with a cubic order of magnitude. So almost the relationship is a cubic relationship between the blade length and its weight. The latest in this area, you can find this in the internet, is a GE Haliade X 12 megawatt turbine. And in this one, the rotor is 220. So basically, the blade is 110 meter long. So you can imagine 110 meter long blade. And then you can calculate its approximate weight. The height of the tower is 260 meter. That's like quarter kilometer almost. And then a capacity factor of 63. So basically, it harnesses a lot of the wind energy. And it can be used to power 16,000 homes. Okay, so I mean, this is the latest in the technology in wind turbine. Maybe there is something new, but I'm not aware of. Now, let's have a look at the wind turbine blades anatomy or the internal structure. So if we start from inside, first you can see we have what we call it the spar and the shear whip. So basically, the spar and the shear whip are the main load-carrying elements. However, the aerodynamic effect, and also it acts as a load-bearing structure, is the skin or the shell, outer shell of the blade. All this, the shell, the spar, and the shear whips are produced from glass fiber reinforced plastic or carbon fiber reinforced plastic, or a mix of them. And on the top of that, you will have a priming or a gel coat, and then you have a finishing finishing coat for the blade, just to improve the surface quality and resist the environmental condition in terms of the ultraviolet radiation. And then at the end, we have the root. This is where the blade is fixed to the hub. And all the loads actually is being carried at this root. So basically, you can expect, as you see here, this is the thickest section in the blade. Okay, and in some areas of the blade, especially at the trailing edge, we use sandwich structure. So basically, underneath the skin, we place some of the foam material. So it can be foam or balsa wood. And the effect of that, you increase the section modulus to increase the bending stiffness of the structure while reducing its weight. Okay, so basically this is the main element. So whenever we do a design, we focus in the shell and the spar design. And of course, we include foam or sandwich structure at the trailing edge of the blade. Now we have to remember, this is the leading edge, and this is the trailing edge of the blade. And then there is one critical element, and actually most of the failures in blades occur at this location, which is the adhesive joint between the two halves of the plate. Now, when we go into the fabrication process, you will see that whenever we produce a plate, we produce the upper shell and lower shell separately, and then we join them using structural adhesive. And if you have any problem with the structural adhesive, then the failure will initiate at this location. So basically, you can just use any adhesive. It has to have specific properties, such as high strength for small and large thicknesses. And also, it has to have low viscosity, can resist environmental conditions. So basically, there is a special class of structural adhesives that are used in wind turbines. Now, when we come into the development phases, as I mentioned, we went through 3 phases. Phase 1, this is where we did reverse engineering of existing blades. Phase 2, we did design and fabrication of wind turbine blades of different sizes. And then phase 3, which is the last phase, this is where we did design and prototyping of small-scale wind turbines. So let's start with the first phase, which is the reverse engineering of existing blades. So basically, when we started the Arab Organization for Industrialization, they were collaborating with NAREA, which is the new and renewable energy authority. So basically, this is the main authority in Egypt that's handling all renewable energy sources. And then they had a problem when in one of their farms, we're running out of the spare blades. And of course, it's a very old it was a very old turbine. So basically, the company is not making them anymore. Then they came to the Arab Organization for Industrialization and just to fabricate or make spare blades for their wind farm. Then they come to us as a consultant to do the design phase, and then they said, okay, we will go through the fabrication phase at their facilities. So when they started, actually, and this is how we started, we have an existing blade. So the best way to go is, this is before, this like in around 2008. So basically, handheld laser scanner was not that well known in industry at that time. So basically, they take it to they take the blade to a 3D scanner using a probe. So basically, they section the blade every say 25 centimeters or 30 centimeters, and then they take these profiles to the to a 3D scanner. They scan the profile, and then they have the upper and lower profiles of the plate, and then at different sections you can have different profiles, and then on a CAD mod and on a CAD software you can just generate or regenerate the blade geometry. Okay, so this is the first phase, and then we working in 2 teams. A team working on the structural design, which was us at BOE, and another team working with the developing the aerodynamic loads on the blade. So at BOE, so basically we start to propose the layup for the blade. So basically, as you can see, this is the layup sequence of the blade at different sections. This area here where we have like this hexagonal shapes, basically this is where we have the foam. So basically you start with 1 layer, okay, or I think this is like 3 layers of fabric, and then you put 1 layer, and then the rest is foam, okay, and then another layer. But as you can see, we decrease the length of the fabric, and then we cover the foam with another layer, and then we continue to build the thickness close to the root, where this is where the blade will be fixed. And at the same time, the group working with the aerodynamics, they develop the pressure distribution at different sections, and they give it to us to implement on the structure of the blade. Sorry. So we conduct the structural analysis. We confirm that we have a safe design in terms of the TSIU, which is like this is like a damage factor or damage parameter used in the design of composites. Just simply, the reciprocal of this value is the design safety factor. So basically, if this like value is 0.2, for example, now, that means that we have a design safety factor of 5. And also we check the tip deflection. So I have to make sure the tip deflection is below a certain value. Otherwise, the blade will hit the tower. Okay, so this was the first phase. So we did like a couple of blades in this project. And then we moved to another phase where we needed to start from scratch. We don't have any blade, but we can specify a wind turbine in terms of rated power, rated wind speed, other design constraints. And then we start the design, both aerodynamic and structural design from scratch. And then just to prove the concept, we wanted to produce a segment of that blade. So this is the design methodology that we followed. Okay, so in the design, we have both aerodynamic and structural design. So basically the aerodynamic design, they develop the blade shape. So basically at different locations, they obtain the aerodynamic profile of the blade. They have what they call the NASA series of profiles. At the same time, we purchased our fabric material. We did material characterizations. And along that, we implement the finite element simulation. And finally, once we have from the aerodynamic loads on the finite element simulations, we came out with the material architecture. Basically, this is the layup of the fabric inside the plate. And then the second phase is the manufacturing phase. So the manufacturing started with the plug, which is a positive mold of the plate, or actually it should be the actual shape of the plate. So with the plug, to be able to fabricate the plug, so basically from the aerodynamic, we get the shape of the plate. And then from that, we produce our molds. And then the composite layup that we obtain from the material architecture or material layup. Then we produce the blade segment. Okay, so this project was funded by the European Commissioning through the RDI project in Egypt. So the material you see here is a special material that's used for making plugs in general, but in wind turbine in particular. This is what they call machinable polyurethane. So it's a plastic material. So it has dimensional stability. It does not absorb humidity. So basically, it's stable under different conditions. So it's a polymeric material. So basically, and also the machining ability of this material is very good, actually, compared to other types of wood. So just as proof of concept, we produced a blade segment. So we produced or purchased these slabs. We did the machining on a CNC machine. This is like a 3 meter long segment of a blade. So this is 3 meter long. So once we're done, we have our plug. So basically, the plug actually is a replica of the blade. Okay, so from this plug, we're able to produce our mold. So basically, this is the different phases. You do finishing, gel coating, then you start to place your composite layers to produce your blade. You make the supporting sides, and then you remove it from the plug. Then you have the mold. This is where you lay down your layers. And then you start to lay down your fabric inside. As you can see, we have foam, and actually the main objective of that project is to incorporate a layer of a polyurethane rubber inside the blade to prevent the foam core from collapsing when subjected to foreign object impact damage. Then we do the infusion process. It was a small segment, so it was easy to plan the infusion strategy. and then you have, sorry, I think I'm this one, okay. And then you fabricate the shear web or the spar, okay, and then you have the two halves, you assemble them using a structural adhesive, and then you leave it for some time just to cure, and then you remove your molds, then you have your blade segment. So, and then you do the, you go through the painting and finishing, and you get your blade segment. So basically, we just went through the exercise to get the fabrication process. Okay, now we take it to another level, which was a quite difficult level, is now to design and fabricate a 25 meter long blade. So basically, in terms of length, the blade segment we produced was 3 meters. So basically, this is like 8 times longer than that segment. The weight, when we look into other designs, like the one in Zafarana wind farm, like we expected the weight to be around 2.5 tons. So it's not a small weight to handle by by our technician. Okay. So we specify also the design variables or design parameters for our turbine. We had our aerodynamic people to work on the aerodynamic design to give us the blade profile and pressure distribution at different locations. And then they give us the blade model to work with. So basically, we know the sequence now. For the spar, we can use a single spar for such a large blade. Actually, the blade width, as far as I remember, it was like 2.5 meter. The maximum width of the blade is 2.5 meter. So we cannot use a single shear web or a single spar. So there were two alternatives, either a box shape or a seed channel, and I think we decided to go with a seed channel. But actually, when we come to the fabrication process, we changed the design because we found it was very difficult to produce the box shape, actually. Even the C also was difficult. So through the fabrication process, we integrated the flanges with the upper and lower skin, and then we built the shear webs and integrated, and then join it with the plates using structural adhesive. Okay, and for that plate, and because we wanted to get the design certification for this plate, so we had to go through the different design load cases of the IEC. So basically, you can see we have, I don't know, so many load cases that we have to test our blade against. And for that, we use, as I mentioned, the open source software that are available at the Renewable Energy Center of the United States. Again, we did structural analysis to, for all design load cases, okay, to make sure that we have a safe design. But we had two design constraints. First, the weight should be less than 2,500 kilograms. Okay, that's 2.5 tons. And the tip deflection under extreme condition should not exceed 10% of the length. So which means that we constrained our tip deflection to be less than 2.5 meter. So basically, you can imagine that the tip deflects like 2.5 meters. Okay, now, if you recall, in the last exercise, we used polyurethane to fabricate our plug. For that project, it was impossible because the cost of the polyurethane is 3,000 euros per cubic meter. So now we're talking about 25 meter long plates. So you can imagine the cost of the plug itself. However, when we searched it and talked with our industrial partners in that project, which was MCV company, they recommended using beech pine wood, اللي هو الخشب الزان يعني. But not any type of a beech pine wood. It has to be highly dried type. So we had to buy it from a specific supplier with dryness of like 90%. So basically you have a 10% of humidity in the wood. And then just to save the material, we used to place like supports and then build or approximate the shape of the blade using blocks of beech pine woods. And then we send this for machining, like we have small blocks because we cannot machine the 25-meter long at once. So we went through the machining process, and then semi-finishing, and then final finishing with a high-quality surface. And then we have to assemble all these 25. So actually, there were 15 pieces actually of these. So we have to assemble all of them and then work on the seams between different parts to eliminate the seams and just make it one smooth surface. And then we start spraying the gel coat, which is the first layer of the mold, and then building the mold, and finally building a steel structural chassis to handle this mold. So now we have first mold, second mold, make sure that they close. There is no shift or gaps between the two molds. And then we start to put our layers, okay, like, as obtained from the structural design. Then we have all layers are placed. And as you can see, actually, in the previous slide, this is the foam layer at the leading edge. So actually, we still have to add one more layer to cover, or two layers to cover this foam layer. Now the process is different. Now we cannot just rely on our experience to do the infusion process. So we have to go to the simulation of the infusion process. So actually, we spent 2 years in our lab training our engineers and technicians before we go through the actual infusion process. It was it was a very long and time-consuming process, but we had to make sure that once we do it, it will be successful, because any failure, that means that we will scrap the material and the molds. So there is no chance for failure. So we did actually, before we go through some simulation, so we had to do some lab measurements. So we measure the permeability of the fabric that we used. So basically, we measure the flow as like a function of time. We use the BAM RTM software to do the simulation of the flow process. And then we start to examine different strategies. So you can see, like, after 4 hours in the first one, where we use a single feeding line with 6 feed points. After 4 hours, still the blue one is a dry area. So we still have some dry areas after 4 hours. So basically, the infusion process using this strategy is not feasible. So we go through different trials, and then the last one that we adopted was 7 feeding lines and 32 feeding points. And as you can see, the full impregnation of the blade occurred in 3 hours and 38 minutes. Now we have to be careful now because of the pot life of the resin. Because once you mix the two components of the epoxy, you have, like, 1 or 2 hours before they go into full curing. And also you have to remember, we're mixing large amounts. So basically the amount of exotherm that's coming because of the mixing process is quite high. And in this case, the curing process will be accelerated. So I had to make sure that the pot life of the mix is larger than this number of hours. And then we laid down our feeding lines. And so basically, this is for the plate, this is for the spar. And as you can see, like, and you can imagine that the amount of work that was conducted during this practice. And then we have the 2 shells. Okay, and as you can see, actually, because we don't have an overhead crane, we used to use 3 forklifts at the same time to open and close our molds. So basically, the process of opening and closing the molds actually used to cost us a lot of money. And then we use structural adhesive. We join the 2 halves And then finally, we get our blade out of the mold. So basically, this is our final product at 25 meter long. It's first in Egypt. And now we have to go through the certification, but I'll leave this to the end of the presentation. The third phase, which is the design and fabrication of a small-scale wind turbines. Okay, the question is that why do we need to focus on small-scale wind turbines? First, the large-scale wind turbines, like in terms of megawatts, 1 or 2 megawatt wind turbines, are installed in wind farms owned and operated by the government and in a very specific area. So when we look into the wind map, the area close to the Zafarana, Jabal Zayt, and Hurghada, this is the area actually where we have a very high wind speed. And this area is suited for wind turbines with high rate of power, in terms of actually the ones that are installed in Jabal Zayt. I think it's they are 2 megawatts wind turbines. So basically, the only one who has the authority to install and operate that these large wind turbines is the government. Now, if we look in other areas in Egypt where we have some relatively high wind speed, so basically you'll find the area to the west and the east of the Nile. So with an average wind speed of 6 to 7 meters per second, and this area actually is far from the national grid. So basically there is a need of electricity in this area, and this area actually there is a potential for cultivation and starting new communities. And this is why we signed an agreement with Reef Al Masri recently, because they are managing the cultivation of this area. So basically, they can make use of these small-scale wind turbines in this area to extract water, underground water. Okay, so basically, the small-scale wind turbines should be tailored for low wind speed areas in Egypt. Now, if you look into any imported wind turbines, you will see that the rated wind speed is in the order of 11 or 12 meters per second. So basically, they are not suited for Egyptian wind speed areas. So if you buy one of these turbines, you will see that they will not produce the rated power that market on them. Okay. The second is that we have to make these turbines affordable for individuals and small and medium enterprises. So people should be able to buy these wind turbines if the price is affordable. So in that area, we actually worked in producing two models of wind turbines. The first is a 5 kilowatt vertical axis wind turbine. Okay. So basically now we know the practice now. The design of the mechanical system is we went through the exercise. The design of the blade is much simpler because blade length is 3 meters each segment. Okay, again, 2 parts assembly, painting, and then this is the assembly process in the workshop. Okay, testing of the assembling of the blades, again, to make sure that everything fits. And then now it's installed in Salhaya near Al-Ismailia and it's operating. Okay, the second one, so basically this is a rough estimate of the cost. Basically, it's expected to cost around 325,000 Egyptian pounds, in that range. The second was a 10 kilowatt wind turbine. Okay. Again, in these two turbines, the rated wind speed is in the order of 7 meters per second. So basically, they are designed for low wind speed areas in Egypt. Again, the same procedure we did: structural design, block fabrication. Okay, but in this one actually, we used HDF wood, just layers. Okay, we assembled them layer by layer, and then we did finishing using hand hand sanding and fine polishing. And then we produced our plates. In this exercise, we integrated our shear web with the blade skin in one infusion. So it was another one of the achievements we did in that one. Then we have produced our 3 plates. This is the mold. Actually, 2 molds actually closed. And then we assembled the plates to the nacelle or the part of the nacelle. Okay, so this is the design of the plate. Okay, this is the fabricated nacelle. So this is the generator. Okay, coupling, bearings, and then the hub. A tower. It's a 18-meter long tower, steel structure. Expected cost around 590,000 Egyptian pounds, with 50% of that cost is coming from local manufacturing. Okay, this is testing the electrical components. So we made sure that all the electrical components are functioning properly before we take it to the field. Okay, again, I'm going to just quickly mention the impact on research. As I said, during the development process, we see some of the challenges that can be addressed through research. The first one, which these 2 topics are published already. So this is were published through the International Mechanical Engineering Congress, IMEC-E, in 2020. Those 2 papers. The first one is the analysis of bolted connection under out-plane loading or tensile loading. Okay, so basically, if you look into this connection in the vertical axis wind turbine, you can see this connection will be subjected to not only shear but large amount of axial load. And then when you look into literature or design codes, you don't see a design procedure for bolted connection loaded in tension in composites. In metals, you find it, but in composites, there is no such a design practice. So we had to go through the design process. As I mentioned, lap joints are well established in terms of design, and different failure modes are identified. Other types of connections composites are emerging, so we need to address these kind of connections also. So basically, you just can go and read these 2 papers. This is the approach. We have an experimental program, and then we use a finite element simulation to validate the experimental work and develop the material failure parameters. And then we studied the different design parameters on the load carrying capacity of the connection. Okay, this is the specimen, an L shape. Okay, this is a finite element model with different details. This is the different parameters. We studied the ratio E over D and also W over D. This is the 2 parameters that mentioned or discussed in this article, but there are other parameters that will be published soon, inshallah. Okay, this is the load deflection curves for several samples along with the finite element simulation. Okay, and just to skip, I mean, this is the different failure modes in in terms of matrix failure or fiber failures. But the good thing is that you can see now our finite element model was able to capture the physical test. So basically, that assured that the finite element models actually is quite accurate. So this is the effect of different parameters. The other paper is the evaluation of the mechanical properties of re-infused or repaired composite. Now, that's why, if I said, during the infusion process, you can get some dry spots, okay, due to, maybe you have a small leak on the mold or improper planning of the infusion process. So you have, either to scrap the whole part, which is very expensive, or you can do a repair process and make use of the part. But before you make the repair process, you have to make sure that the repair process will not affect the quality of your product. So basically, there are some work actually in the repair of damaged composites. But in this one, we wanted to study the effect of the orientation of the fabric on the repair process. So So when we look in the literature, there are two techniques to repair, either using a scarf repair or patch repair. Each one has its own advantage and disadvantage, and the selection process depends on many parameters. So we're not going to discuss that now. This is our experiment. So basically, we used to create an interface or produce a part with a specific interface. Like here, this is a 90-degree interface. We can make one also at 45-degree. Okay, so basically, we make this part using hand lamination or hand wetting. And then the other dry area we're producing using vacuum infusion. So also we get like, hand lamination versus vacuum infusion. So because you can do the repair process using either technique. And then we studied the tension and flexural strengths. So, and we observed that there are some effects to the interface on the repair process. Okay, so just to wrap up, we during this journey, actually, we concluded 3 points. First, the work that we conducted on design and fabrication, actually we aimed on certain objectives. First, we needed to develop the know-how, because we don't have the know-how here in Egypt, at least, as far as I know. So basically, we needed to develop the know-how in the design and fabrication of wind turbine blades, and I believe that we have this know-how to some extent. We need also to build human capacity in terms of trained engineers and technicians on the design and fabrication, and I think we succeeded also on that. And also now, if it's possible now, we can start our own company in the fabrication or design and fabrication of wind turbines in general, and I think we are in the process of doing this. Also, what we found also is with proper training, engineers and technicians were able to master the fabrication process. As I mentioned, that we spent almost 2 years in lab training our engineers and technicians on the infusion process in different scales, from sample size to a 3-meter long segments. We did all kind of training before we take them to the actual process. But we still have challenges, and these challenges actually it needs some sort of national efforts. First, testing and certification. Just to mention, when we tried to obtain the certification from one of the agencies, I think they told us we'll give you only the certification on the blueprint of the design. And I think the number for that certificate was around 60,000 euros just for this. We're not talking about the manufacturing or testing. No, it's different. Testing by itself, we studied the possibility of making a testing facility or a testing setup for the 25-meter long blade. And I think it came around millions or so. So it's very expensive actually. But it's not as easy as that, because if you build your testing facility, then you have to approve it from other agencies. Okay, so basically you have to certify or get certificate for your lab, an ISO certificate or other funding, from other agencies in your lab. So testing and certification is a problem if you need to get our product into international markets. Still, all fabric materials, chemicals that we use in the fabrication process, they are all imported. I know there is a glass fiber manufacturing company in Ain Sokhna, I think it's Juchi, but I think all their production is for export. They don't get it into local market, as far as I know. Maybe it's now situation may be different. Another problem is that, as you can see, the cost of the turbines ranges from 300,000 to 600,000. And I think, like, for individuals, people like, with like, small farms or so, it will be difficult to them to get one of these turbines. So basically, funding these turbines is a problem, especially if the farm, they don't have what they call it, like, like the full legal documents, that will be accepted by banks for funding. A main problem for us is the electrical components, generator, controller, inverters. We don't have these in local markets. Still rely on importing. And actually, if you go back to the previous slide, you will see that the cost of these components almost like 50 to 60% of the total cost of the turbine. So basically, if we're able to produce these components in local market, it would be great. And I think, Dr. Mohammed Abu Aqil will have a presentation that touches in this topic in the coming few minutes. Thank you for your attention. I think I went beyond the planned time. I apologize for taking that long. And if you have any question, maybe Dr. Mahmoud will postpone the questions, maybe, or cancel the question session. And if you have any questions, just send me an email, and I'll be glad to answer your questions by email. Thank you.
Thank you very much, Professor Mustafa Shazli. It was a real pleasure and a great journey to listen to all this information and to listen to the journey that you took at PUE to first get the knowledge and then apply the knowledge, and trying to expand this knowledge to students and to other researchers in the team. We were actually planning to have a discussion immediately after that. So actually the discussion, if you let me share my screen, the discussion is about these latest challenges that we spoke about it in the presentation. So let us see. So the first challenge, as it was discussed, is the certification. I just would like to ask Professor Shazli, is it necessary to make this certificate if you're going to use it for domestic or for internal use inside Egypt, or it's just if you want to export your product?
Actually, to do it right, yes, we have to get certified also if you want to get into local market. I mean, we can do testing, of course, but this is just to verify our design, to make sure that design and fabrication have the enough quality for that turbine to survive. But yes, definitely we need to get certification for our products, just to make sure, everything on the safe side. And if you want to get into international market, definitely you will have to have these certificates.
Okay. I don't know if Dr. Muhammad Atiyah is still with us. Are you there, Doctor?
Good evening. Salamat Mustafa. Salamat, Dr. Shazli. I think some of you here know, some of you here know Dr. Shazli is my classmate, and we graduated 5 years ago. So,
okay, yes.
He's a very, very, very dear friend. So, we used to sit together in
I'm very happy that we could bring you together in one meeting. That's our aim, to put brilliant minds together.
So on the certification, I'll just introduce myself quickly. Muhammad Salah Atiyah. I work for General Electric Renewable Energy in Schenectady, New York. And over the last 10 plus years, I've been working on different responsibilities regarding blade design, failure analysis, reliability assessment, and as well as new technologies. So looking into what's next on blades. And I've been on and off talking to Dr. Shazli about all these developments at the BUE along with Dr. Bahieddin. So it's really impressive. Let me say this. So my take on the certification issue is it's not just for the international market, but as Dr. Shazli pointed out, it's also for domestic market, proving your design, getting your design judged by an independent agency, be it DNV, GL, or TÜV Nord, or other certification agencies. But the other factor that is playing here in a market that is becoming more and more integrated into global economy, if you go to a bank, like if I'm what do you call it, like a energy producer, something like Edison Pacific in the US or Nextera, or like I'm selling electricity. Typically, I will go to a bank to request funding to support buying these wind turbines. How would the bank ensure its interests and in this project? The most common term here, or the most common way, is through certification. I need to make sure that whatever is being sold here or whatever is offered is actually certified, and this way I can ensure that I can guarantee my investment in this project. So it is an expensive and painful process, yes, especially for a new design office. I will consider the BUE here to be a design office because you are establishing the ground rules for future dealings with whatever entity you are certifying through. So it is kind of the unavoidable evil that we have to go through.
But I'm actually wondering, Dr. Muhammad, that in the past, before the civilization, there were like windmills all over the country, and they were using the wind power to mill the wheat, and it never had needed a certification. Why certification is exactly needed that much? I see also Dr. Muhammad Saad want to ask something.
So I will simply point out that 30 years ago we were dealing with 10 meters blade lamps sitting in the middle of the desert. Now we are dealing with literally 100 meters plus blades that are flying within a mile, or within few kilometers from human populations. And this is a very critical topic when we formulate the reliability problem and the cost problem of wind turbines. It's not just the mechanics part. The economics part is heavily affected by what is the human cost. So when I say that I will allow my blades 1 in 2,000, that's the reliability, that's the probability of failure that's allowed. That is 1 in 2,000 turbines to fail. That is not a number that came just like out of just like some guesswork. There is some heavy calculations based on historical data and math involved here. And personally, I saw like think of 50 tons flying mass. Like what is the flying range that can affect us here, and what will be the impact of one lost human life here? So it's not not an easy.
Some videos on YouTube were really shocking about failure happening to wind turbines. It's really shocking.
Exactly. So certification is required for either funding or safety. Maybe there are other factors that I'm not personally aware of. I know that even like GE as a company, we sell sometimes turbines that are not certified, but these are decisions that are based on very careful economic decisions, and also some of the working relation with our customer. So in some cases, we'll say, okay, you guys have good history of producing this rotor, so okay, we can skip certification for this project. So again, this is not like an absolute must, but it is at least as a starting point, it is required.
Thank you very much.
Thank
Dr.
you.
Muhammad Saad, do you want to ask something?
Yes, please. Okay, thank you so much. First of all, yes, good evening. My name is Mohammed Saad, the Principal Technical Specialist at Technology, spin-off company from Imperial College in UK. First of all, I would like to thank Professor Chazli very much for...
We have a problem hearing you, Dr. Muhammad.
Already?
We hear you.
Okay, just...
I think it's a problem with your mic.
So you cannot hear me?
Sometimes yes, sometimes no.
Okay, just 1 second. What about now?
It's perfect.
Okay. Yes, I will start from beginning. So my name is Mohammed Saad, the Principal Technical Specialist at Information Technology spin-off company from Imperial College London. First of all, I would like to thank Professor Chazli so much for giving us this great opportunity to catch and this excellent information. This is not my interest area for research, but to be honest, yes, I have got some good information about this. And actually, this is the first time also to hear that there is kind of knowledge or knowledge generation come from university and it can be commercialized. This is what we have done actually in UK. So we develop a process and then we open a spin-off company, which I'm working now. So this is really great achievement in Egypt and of course in academic research. And I know Professor Chazli, I think from quite 6-7 years. So I'm pretty privileged to work with him supervising some master students. I just have just because I said in the beginning it's not my interest or research area, but I will just have very quick question. During the mold for this large wind turbine blade, is it surviving from any distortion? And if so, how to compensate this? How to predict and to compensate it in there? Because I think it is the consistent angles of the three blades, I think, are essential, or it is essential. I'm not sure if this is eligible to ask this kind of stuff. Okay, thank you.
Dr. Muhammad, if I get your question correctly, I mean, you think there will be some distortion during the manufacturing of the mold itself?
No, I'm asking if there is any distortion, and how to measure this? How to measure the accuracy or geometry for this large turbine? Because I think this angle is consistent for this, or for the geometry for these three blades.
The angles, you mean the twist angle or the pitching angle? I mean, of the three blades.
Yes. Because what I'm asking, because Professor Chazli, because we had a program in BAM stamp. You know, ASI has a BAM stamp. And BAM stamp has a version. It's called the BAM distort. Exactly. To I think because I had a guy modeler working in this because simulation of composite material and forming of composite material is really difficult. It's not like a metal at all. It's really challenging. So and the clients asking about this distortion happen. I'm not talking about as an angle or any distortion in geometry.
Yes, you're right. We actually in that project, especially for the 25-meter long we did not measure the shrinkage due to the after the fabrication process, but we experienced that shrinkage process because we're using epoxy. And epoxy, I think the shrinkage, I think it exceeds that of the polyester, as far as I remember. And yes, after the infusion of the, the two halves of the blade, actually we start to see separation of the part from the mold. So yes, we experienced some of this shrinkage. Yeah, but we did not actually do the model for that. But yes, we did that. We observed that. But actually, we were worried more about the matching of the two halves in terms of the mold itself, because in a 25-meter long, I mean, if you get 2-3 millimeters difference in each segment, in a 15 meter long, in a 15 segments, then you're talking about 3-4 5 centimeter difference between the two halves. Yeah. So yes, but we experienced this kind of shrinkage, but we did not account for in the design or the fabrication process. Now, if we if we go back, I mean, if you ask me, if you are going to do the fabrication of the 25-meter long again, I will not do it in one shot, because actually what we did, we placed all the fabrics, including the root region. Actually, the thickness of the root was 8 centimeters, and as far as I remember, the number of layers was more than 100 layers, and it was a problem for us to design the infusion strategy for that section. And actually, the separation started at that location. So now, if I go back and I'd like to do the infusion process, I will just do the infusion for the main layers, which actually span the full length of the blade. And then I'll do the rest of the layers to build up the section of the root, just to avoid such a high shrinkage effect at the root. Yes, but you're right. Shrinkage is one of the problems with the epoxy.
Exactly. Just yes. Thanks so much. Because in aluminium, we doing, for example, hot forming and then quench. And during quench, Professor Shazli, we suffered from shrinkage, and we call this thermal distortion actually. And we need to just know how to predict by simulation the correction force required to bring the distorted section into the line for assembly of purposes or for two parts, as I said. Okay, thank you so much. Thank you so much.
Thank you, Muhammad. Thank you.
Sorry, I was just muted. The next challenge was about the fabric materials, that it's all important. Why it's not possible to produce it locally? Are all the materials completely imported from abroad, or the fabrication and the weaving to make the weaved material together is done abroad? What's the problem, Professor Shazli?
Frankly, I don't know, but I think we don't have this technology. There is no interest for this kind of materials in Egypt. I mean, we don't use it in many applications so far. I mean, as far as I know, most of the applications in composites are for small tanks, some of the yachts, some of the boats, maybe for toys for kids. I mean, that's what you say in the playground.
Yeah. So we may say that the market for composite materials in Egypt is just taking baby steps at the moment.
Yeah, maybe, yes. But as I mentioned during the presentation, there is a company in Sokhna it's Jushi. They are actually making glass fibers, but they make the yarns only. They don't do the weaving process.
They do or they do not do the weaving?
No, they don't. They don't do the weaving. They just produce the yarns and then they export all their production. Chemicals, like high performance epoxies. Okay, we have to import them. Okay, there are different suppliers around the world. In Egypt, there are now like 2 or 3 companies are making some of the resins. We have not tested them. I mean, to judge their strength or quality. But I know the كيماويات البناء الحديث. It's a new modern chemicals. Okay, maybe it's not the true correct translation. They have their they can produce some of the resins. Also, Sika, it's another company in Egypt. They have chemicals, and also just for your information, Sika they sell sheets of carbon fiber. So basically, if you need a sheet of carbon fiber sheets, they sell it ready-made, but they don't sell the carbon fiber itself. I mean, just they infuse it with resin and then they sell it. I think it's used in construction, basically.
Yeah.
In terms of structural adhesive, we don't have any company in Egypt that we can rely on to get the structural adhesive.
Concerning the funding, I knew from some colleagues working in the field that El Swedi, he started a project to produce the towers that carries the wind turbines, but then they stopped for a while and now they are back again. So I think it's like seasonal production, because it depends on if the government will make a new farm or not. Do you agree with that, Professor Shazli? Or
as far as I know, Sweden they had a partnership with a company in Spain, and I think they took over that company. I mean, but I know they used to produce the towers for the wind turbines, but I'm not quite sure if it is for local use or for exporting. But I think it's just for the towers. But bravest effort, as I mentioned, the Arab Organization for Industrialization, actually, they had great efforts around 2010, like 2009, to actually get into the renewable energy sector. And they now established actually a company. It's called Arab Renewable Energy Company. But we're focused now actually more on solar energy. They produce solar panels, or under license, I guess, or they do the assembly process for this kind of panels. But actually, they wanted to get into the wind energy sector. And they trained a large number of engineers in that area. They actually get an agreement with, I think, LM to produce one of their turbines, which is a 2 megawatt in Egypt. And then they, I think they had phases for this agreement, but because of the changes in Egypt and all that, the process was the project was cancelled. Okay, one of the main reasons, again, I think I mentioned that during the presentation, the sole buyer for this kind of turbines is the government. So basically, they have only one customer, and I think the government actually, when they get this kind of projects, they get it through loans from other other countries or so. So basically, they will not be able to sell their turbines in Egypt only. So that's why they canceled the project.
Yes. Sorry, Dr. Atiyah, I have another question for you. Just trying to imagine if there is a multinational company that would like to use Egypt as a base for producing wind turbines
Mhm.
and exporting it to the Gulf area or Saudi Arabia, wouldn't that be economically better than producing it in the US or Europe and then transporting them to these areas?
Well, you are bringing us the pain point, the everlasting pain point. Why are we not doing what India and China do? So, majority of our production, and here I will be speaking for GE and LM Wind Power. Majority of our production is actually in India, China, Turkey, Mexico, Brazil, and only few are produced in Europe or North America. Okay, so the answer is definitely yes. That is something that we are looking for. It is, I think, the barrier, like probably, like there are barriers that go beyond the topics covered in this meeting, but I would say what Professor Shazli mentioned about incubating skill sets necessary to attract a multinational company. A multinational company will bring funding and equipment, but human power, that is probably the most valuable asset that has to be there. And this is, we all know, this is available in abundance in China and in India in particular. And I don't see a reason why don't we have the same story in Egypt. Good technical education. This is an excellent project. Like this is an excellent how to put it, like know-how development project. This is how you learn how to build things. So yeah,
I can tell you that what I've seen in Cairo University at metallurgical department and in Modern Academy and production department, engineering department, I don't think we have any curriculum that helps the students to get the skills to work in that field. Do you think we should improve our curriculum to make them ready for that field?
Yeah, I mean, I heard like at least in Cairo, Dr. Said Kasib, years ago there was an agreement, I think, with University of Kassel in Germany, like a master in renewable energy. I don't know the topics that were covered, or more importantly, the know-how. And let's here differentiate between academia or like research as a topic, but or actually developing a know-how. What Dr. Shazli showed here, that is like kind of worth its gold. How to put the runners, how many feeding tubes, ensuring that I will not end up with dry spots. There is some science behind this, but end of the day, if you do not practice it, there is no way, there is no hope in hell that we'll get anywhere. So it's a combined thing, apprenticeship coupled with education. We have to have like an initiative. We have to have students being trained in the, let's say, in the secondary, in the technical education discipline, rather than being trained for machining only. How about looking into these topics? Because this is a worthy topic for sure.
Yeah, we have in our organization, in our private university, we have some graduation projects, for example, working in renewable energy and but in parts like solar cells and so on. I have found, I don't know if you can see my screen, I have found this course by Ministry of Electricity and Renewable Energy could be interesting for the students maybe, that they provide training in the field of wind energy and renewable energy in general, wind and solar and so on. So I didn't go through it and see details about it, but I think it's worth visiting. I will put it in the presentation so people can also have it in the version that they will get after the meeting. Okay, I don't want to make the meeting so long for everyone, so I will skip the other parts of the discussions that were planned, that we discuss also electrical components and how can we produce longer blades. I know it's a growing demand for bigger and bigger wind turbines. Also, we were planning to discuss improving manufacturing methods, and maybe there is a better way to produce it that is cheaper and doesn't have so much expenses. So please share your ideas in the group on LinkedIn, and after putting the recording of this meeting, I just would like to invite quickly in 5 or 10 minutes Dr. Muhammad Abu Aqil will tell us about a project that he's doing at Modern Academy, actually very innovative project, and he has got a really generous funding. He will tell us about that and what he's doing with his students in this field. Can you hear me, Dr. Muhammad Abu Aqil?
Thank you, Dr. Mahmoud.
Please try to share your screen now.
Yeah. It's a pair.
Yes, we can see it now. Please go ahead.
Thank you for giving me this opportunity. I would like to introduce a talk about some wind turbine problems and the solution. We are going developing at Modern Academy. This project is funded by the Academy of Scientific Research and Technology in Egypt, and carried out at Modern Academy for Engineering and Technology. In this project, also 12 undergraduate students are doing their graduation project from Department of Manufacturing, Engineering and Production Technology. In the past decades, wind energy has become an increasingly attractive source.
I'm sorry. Actually, it's frozen. Your presentation. Did you make full screen of the presentation or not yet?
Yeah, it's full screen.
I can see only the first. Yeah, now the cursor is moving. Please try to put it on full screen. Yes, you have to stop the share screening and make it again, maybe.
Second.
Now we can see it. Yeah, and when you make the full screen, is it working?
Is full screen in it now?
No, it's not. You have to stop the share screening, and when you click it again, you have to choose the one at the total left of the choices. You have to choose the one that will share whatever anything will be on your screen.
Okay.
So please stop this share screening now, and then try to do it again.
Okay.
And then choose the one at the total left. Yes.
That is okay.
It's still not full screen.
Wait.
Okay, so maybe you can show us it without full screen if it doesn't work.
I will full screen or no?
No, it's not working with full screen. So please try to show the slides just on PowerPoint without full screen.
It's okay?
Yeah, we can see it like that.
Yeah. Thank you for interesting your presentation, Professor Mustafa Shazli. I would like to talk about some wind turbine problems and the solutions we are developing at Modern Academy. This project is funded by the Academy of Scientific Research and Technology in Egypt and carried out at Modern Academy for Engineering and Technology. In this project, also 12 undergraduate students are doing their graduation project from Department of Manufacturing Engineering and Production Technology. In the past decades, wind energy has become an increasingly attractive source of energy generations. As we can see in this figure, the wind power capacity has increased very much. On the other hand, there are different kinds of wind turbines, such as horizontal axis and vertical axis wind turbine, as shown in these figures. However, an important part in the horizontal axis wind turbine is the blade, which is subjected to different loads and should be reinforced in innovative techniques. As wind turbine plates are exposed to different loads which are dangerous to the blades, there is constant need to improve the fracture toughness as well as fracture mode and failure mode of these plates. This is why in our project we modify the blades material through adding nanoparticles inside the polymer matrix composites that is already reinforced by hybrid carbon and glass fiber reinforcement. This work we are going to use compression molding technique. As we can see in this figure, in the current slide we suggested mixing nanoparticles such as alumina and graphene nanoplatelets with epoxy or inside epoxy to reinforcement the plates. This is done by high frequency sonifications. Then we add all materials in compression molding techniques. We expected this methodology to positively affect the blade and improves its fracture toughness properties. Another important part in the wind turbine is brush. In the brush in the generators, because of motion transfer, it's exposed to high wear, friction, and thermal conditions. The brush of the wind turbine are usually made by copper. However, they have no satisfactory properties to face all these conditions. So we should take in consideration the material selection to produce the part. So in our project, we are going to use powder metallurgy route to produce the brush by adding nanoparticles such as alumina and graphene nanoplatelets and in matrix of copper. The mixing is done by mechanical alloying and then compacting by compression, cold compaction process, then sintering stage by inert gas of furnace. This is two methodologies improving the brushes and brushes by graphene nanoplatelets and alumina, and the plates improved by alumina and other carbon nanotubes by nanoparticles in order to improve the brushes and blades in the wind turbine. Thank you very much.
Yeah, thank you, Dr. Muhammad Al-Aqil. So actually, they got about, I think, 30,000 Egyptian pound, which is like 1,500 euros, I would guess, in order to support the students, buy the material and do these things. They are going to do lots of characterization by scanning electron microscope, transmission electron microscope, and so on, and make the mechanical testing for the blades that they're going to use?
Yeah. After finished all stages of manufacturing, we suggested some characterizations. The divided characterizations can be mechanical characterizations such as tensile, bending, and fatigue. On the other hand, the scanning electron microscope or microstructure characterizations by optical microscope and or scanning electron microscope in order to obtain the optimum characterizations of the production cases.
Perfect. Anyone has any questions for Dr. Muhammad? Yeah. So thank you very much for your patience during this whole time. I would like to wrap it up and announce the next, what's going to be next. We are going to meet after about 1 month on 28th of May, and we are going to speak more and try to invite people from industry to speak about different factors that globally affecting the production of wind energy. These factors, as we can see, are many: social, economic, geopolitical, environmental, the need for public policy to help and guide the policymakers in order to make spread for this technology in Egypt and the Middle East and North Africa. In Middle East and North Africa, then we have to try to invite partners in this field or the big players in this field in order to tell us about their experience. We are going also to speak next time about what should we do in order to produce complete wind turbines in Egypt. We will do it from the business and industry point of view. As we can see, in the year 2018, globally, the new installations were done by these companies, arranged by the number of installations that they have done. You can find here all these companies. The reference I had, sorry, it was in 2018. I couldn't find one in 2020 or 2021. I thank you very much for your patience and your help for this to come through. I thank very much Professor Mustafa Shazli and Dr. Muhammad Atiyah and Dr. Muhammad Saad for their contribution in the discussion. It was really helpful, and we hope to see you next month.
Thank you, Dr. Mahmoud, for your efforts. I really appreciate that all the effort that you spent to make this event actually a well-organized event. Thank you.
Oh, thank you very much.
Thank you very much.
Okay, thank you. Just great.
Maybe next time we can have real croissant and real coffee, and that we can meet after the pandemic, I hope. So I wish you all a perfect good evening, and for those that are going to fast tomorrow in Ramadan, happy fasting, and see you next time. Bye.
See you. Bye.
رمضان كريم. السلام عليكم.
وعليكم السلام.